Okay, today students, we're going to be taking a look at section 14.3 entitled Secant Lines. A line that intersects a circle in exactly 2 points is called a secant of the circle. You can find the measures of angles formed by secants and tangents by using the following theorems. So the first, if a secant angle has its vertex inside a circle, then its degree measure is 1/2 the sum of the degree measures of the arcs intercepted by the angle and its vertical angle. The depiction below, that particular example that you see, I'll be able to speak more specifically as to how that theorem plays out, but also the next theorem possibly. Together, I think both theorems will be used pretty thoroughly in our lesson today. If a secant angle has its vertex outside a circle, let's differentiate from the first theorem inside a circle with the vertex versus outside the circle with the vertex. Then its degree measure, again, is 1/2, but in this case, the difference of the degree measures of the intercepted arcs. So up above, we were noticing that more specifically, it was 1/2 the sum of the arcs intercepted, while here 1/2 the difference of the intercepted arcs. Okay, so example, find the measure of angle MPN. So M, this point being on the circle, P outside the circle or exterior to it, and then N, of course, again on the circle. So this angle right here, angle MPN, is what's being asked to be calculated. So it says you can use the last theorem or second theorem above, which again, if you recall, spoke to the vertex outside the circle as opposed to inside. So point P is the vertex of the angle that we're trying to figure out here. And because it's outside the circle, we're going to be taking half, in this case, the difference of the intercepted arcs. So they did tell you one arc of which MN is given as 34 degrees, and then the other arc RS as 18. Now, you're not going to be subtracting the smaller minus the larger arc. You're always going to be taking the larger minus the smaller. You want a positive answer in the end, not a negative, of course. So when you do the math, 1/2 simply of the quantity arc measure MN minus arc measure RS, 34 minus 18. And therefore, if you do the math, half of what? 34 minus 18, which is 16, ends up being 8. So the measure of the angle is simply 8 degrees. Let's move on. So as you can see, the 6 questions that we're about to take on here, the first 3 of which asks for the measure of each numbered angle, as we kind of already discussed in the example up above. But for problem number 1, this is a little bit different in the sense that, well, because the angle in question, in this case angle 1, has a vertex of which is inside the circle, we're going to be applying the first theorem. So I'll scroll back up just to repeat again. If a secant angle has its vertex inside a circle, then its degree measure is 1/2 the sum of the degree measures, not difference, sum of the degree measures of the arcs that are intercepted here. So as it turns out, measure angle 1 should be equal to 1/2 the sum of the 2 arcs of 52 and 40. We'll do that math, clean that up a little bit, see what this ends up. Okay, so if we do the math, for 1/2 of, we got the sum of the 2 angles of which 92 degrees. And that then ends up being, if we just simply do the math, half of 92, of course, 46 degrees. Wonderful. So that's the angle 1 measure. We could also argue that this angle is also 46 degrees, because they happen to be vertical angles. If you remember that vertical angles are congruent. Okay, number 2. So number 2 actually speaks to a situation where the vertex is not inside nor outside the circle, but is actually on the circle. Now, if you recall from a previous section, inscribed angles of this nature are going to be justified as follows. We're going to take the measure of angle 2 and note that it is always equal to half of the angle, in this case of arc of course in this case of 134 degrees. Simply the angle should be half of that value, so we just divide 134 by 2 or multiply it by 0.5, same deal, 67 degrees. So a little bit of a neat twist on not inside nor outside of the circle, but on the circle. We're actually not subtracting nor adding, of course. Nothing, just a single arc to interpret and utilize. Okay, so number 3, back to the new theorems. So angle 3 is, I would argue, pretty obviously outside the circle, of which the vertex is right there. We do have a combination of arcs, though, to consider. So we have an arc of 100 degrees. This is one of 2 arcs that we're going to have to use in the context of the actual theorem when I do my subtraction versus addition. Now this will be a subtraction, not an addition problem, because again, it's outside the circle. So we'll set up our equation as follows. The measure of angle 3 will equal 1/2 the difference of 100 degrees at another angle. Now I'm going to leave that angle open for the, or arc, excuse me, for the argument of this not being known yet. This arc is really the unknown here. I'll call it x. But let's think about this. Based on what the information is highlighting here, I do have an arc of 110 degrees. I do have an arc of 100 degrees. I do have an arc of 80 degrees. I don't know arc x. But if you think about how, well, with a full circle and its revolution, the arcs of which should end up adding together to be 360 degrees. So that should be enough for us to calculate the arc x. Okay, so let's do that. I've got 100 plus 80 plus 110. So in effect, that should be fairly straightforward, I would argue. So we've got 180 plus 110. So that's easily 290. So we can simply then subtract 360 minus 290. And that's easy enough, of course, so 70 degrees. Okay, now remember, that just tells us the smaller of the 2 arcs that we're still going to have to subtract. When we do that, we're going to take half now of what? 100 minus 70, which of course is 30 degrees. And that then lends itself quite nicely to a 15-degree angle. Again, that's the exterior angle or angle outside of the circle. Moving forward, in each circle, find the value of x. Okay, so again, this is a simple idea of which we have, it looks to be an angle in the inside or interior of the circle that's been formed, thanks in part to, well, we've got a 130-degree arc. We have an x degree arc, which again, we don't know, but we're going to have to find, of course. But an angle inside of which we know is 100 degrees. So the formula goes as such. If the angle's inside, I'll go back to theorem 1 up above. If it's inside, you'll take 1/2 the sum of the 2 arcs added together. So 100 should be equal to 1/2 the sum of 130 and x. So if we set it up accordingly, even though x is the arc as opposed to the angle that's unknown, that's still okay. We'll be able to solve. So from what we remember, hopefully from algebra, we're just going to multiply both sides by 2. That's simple. Multiply both sides by 2, and actually, let me erase this 2. You easily just cancel these. Multiplying 2 by both sides leads to, very nicely on the left side, 200. And on the right side, these already are canceling, as you can see, and I'm left with then 130 plus x. Subtract 130 from both sides, and you should end up with 70 degrees for the arc length, as you see marked up as such. Number 5. So this particular problem actually is very similar to number 2. Here's the vertex. This is actually another question from a prior section. This is technically an inscribed angle. This is not one of the two new theorems that we're applying here. The math does look like the following. So the measure of angle Z should be equal to 1/2 of 1/48. Okay. So quite frankly, the problem does relate nicely back to number 2. The application is pretty much the same idea, actually, in which you just simply divide 148 by 2, and the inscribed angle of 74 degrees is simply what we're looking at. Number 6. Moving on, last problem. Apparently, we've actually seen a problem like this already today, but in the sense that, like number 3 and the example up above, this uh, angle of 20 degrees is formed by the two secants that we can see cutting through the circle. These again are called secants. Just to highlight definitionally what that is in fact. So 20 is equal to, because it's outside the circle, why don't we scroll up one more time? Second theorem speaks to what? Half of the difference of the two intercepted arcs. So half of the difference, 70 minus x. And in this case, we'll more though like number 4, we'll multiply both sides by 2. And these are going to cancel, which lends nicely to 40 equals 70 minus x. We can actually subtract 70 and then divide by a negative, or we can add x and subtract 40 to get 30 degrees. Either way, you'll end up with 30 degrees as your resulting arc. You want to double check, and you can double check any of these questions for that matter. 70 minus 30, that's 40, divided by 2 is 20. Just to highlight, back again, as we wrap things up here, um, this particular section speaks to how these secant angles are formulated. And although we've seen secants in every single problem today, not every single problem actually related to the two new theorems, as we saw in numbers 2 and 5. But yes, all other questions besides those two spoke to either adding the two intercepting arcs and dividing by 2, or subtracting the two arcs, depending upon where the vertex landed.